We're gonna get started. So big assignment is in. You're getting a study guide tomorrow for an exam a week from tomorrow. I think I've been pacing this class a little bit faster than I've been intending. I still need to look into that, but my guess is that the exam won't quite cover as much as we've gotten to. I'll have to see that and verify it for sure, but I don't really want to, if we have been moving a little bit faster, I don't want to shove more content into exam 2 than has historically been there. I try to keep each exam covering about the same amount of material, so that would just mean that there's material that we've covered that won't be on the second exam, if that's the case. I have the memory of a goldfish, so I actually have to go look at it to know. Any questions about anything before we dive back into Turing machines and continuing with those until we start getting into the theory of computation? Let's do it. So yesterday we were looking at Turing machines. We defined them, we looked at what they can do, we gave some visuals like this for figuring out, okay, how do we specify a Turing machine transition? How do we visualize a Turing machine transition? And we found that Turing machines are kind of cool, I guess. We'll see if we change our minds on that as we actually have to write Turing machine programs ourselves. That usually becomes the breaking point where people say, this was cool until you made me work with one. But we also looked at what a transition graph would look like for them. So just like with an NPDA, we're looking at triples. We have the character that we are seeing on the tape, the character that we are writing on the tape in its place. It can be the same character doing a no-op. And then we move either left or right on the tape. There was also this symbol called a blank, which we're representing with a square that says it's the equivalent of a null. There is nothing there. And the only reason we would have a nothing is if that is the end of the input, beyond the end of the input, and or beyond the end of, on either side, basically. You can start to utilize that space to do your work because the Turing machine's tape also becomes your working memory. It's your storage and your memory at the same time. So we looked at as well an infinite loop because we couldn't really get those in any other state machine that we were doing or utilizing because we would eventually reach the end of the input and then fail. And since the input had to be a finite length, there was no way for a DFA or an NPDA or any other state machine that we've looked at to actually go into an infinite loop. However, here we can absolutely go into an infinite loop because we're not reading from an input, waiting for something to terminate. We are reading the input and we can move left and right. And as soon as we can move left and right, we can get in a move right, move back left, move right, move back left, make no changes. And that process never terminates once we get into that concept of an infinite loop, which is why we can write them in our programs. We talked about instantaneous descriptions, about how to make use of and describe the process of moving from one state to another while also representing the material, the information that's on the tape. So we said we're going to look at every element to the left of where the current head is pointing on the tape. Then we're going to write the name of the control unit's state. And then we're going to write the rest of the input on the tape. And that becomes the state of the Turing machine, as you can represent it in a single string. Then you can start putting those strings together with the turnstile symbol to say we can get from this state to that state to another state to a final state by some legal transition within this Turing machine. So we found that a single transition like this was able to be shown in instantaneous description form as such. Any questions on what we covered? I think that's where we ended. We may have done the next slide, but again, memory of a goldfish. All right. I think we did actually cover this now that I'm looking at it. We said that the input for a Turing machine acceptor starts on the tape. Machine starts in its initial state. Read-write head is looking at that first character of the input, where the rest of the input is to the right of it, and there are blanks to the left of it, and then blanks again past the end of the input. we decided that we're gonna accept this input if the Turing machine reaches a final state and halts. And then we said that blanks are not allowed inside of the input, because otherwise we reach this ambiguity of, is that blank the end of the input, or is there more input past the end of that? And there's no way to resolve that without infinitely searching the tape. And since it's infinite on either side, that process would never terminate. So we just cannot allow it. We can indicate failure if we halt in a non-final state or if we enter an infinite loop. And remember that if no transition is defined, we halt immediately. So let's prepare to write our first Turing machine program. Here it is. We're going to give you a regular language to start, 0, 0 star. So this is a regular expression. How could we write a Turing machine to be able to do this? So you're going to need to specify the states and the transitions, assuming that the input, whatever the string is, and you can assume that it's only zeros. There are no ones in this language. So the read-write head is at the first character of this string. The first question you might want to ask is, how many internal states are we going to need for this machine? Any thoughts on that? It's here 2, and we have 2. I love that because it's right. 1 is going to represent the searching state, and 1 is going to represent the termination state.
Is the alphabet just 0, or is there another letter within the alphabet?
Let's actually see what I have planned. I'm going to assume that it's just zeros for the moment. Which also is equivalent actually to there being ones, because you don't need to specify any ones. We're not looking for any ones. So if we see a 1, we don't handle that transition, we'll immediately halt and reject. So the Turing machines would actually be identical to each other. If we needed to consider a 1 or not consider a 1, because we never need to consider a 1 in the language. We see a 1, it's not in the language.
It just changes what I say on each edge.
Right. Well, if you don't specify the transition, then we immediately halt and reject.
It's like an NDA or the
The NPDA or the NFA.
NFA.
Yeah. Yeah, either one of those works with regards to, you don't have to have a total function, you can have a partial function.
Will you always need a minimum of 2 states to distinguish between something else and accepting?
Likely, yeah.
That's not 2 factorial, right?
Yeah, that is 2 states, although 2 factorial is 2, so it doesn't matter.
It's true.
The power of space.
For once, exclamatory and the mathematical factorial mean exactly the same thing. I can approve of that. There was a joke I saw about that. What was that joke? I really want to find it now. I'm gonna look for it while you keep working on this, see if I can find it.
Wait, what's the joke about?
It's factorials and exclamation points. Oh yeah, there it is. Here it is. I'll keep right on. I saw this and I thought it was hilarious. This got me so happy.
I get it.
Yeah.
I get it.
That's pretty good.
Don't even need to do the arithmetic up top.
Yeah, the best jokes, you don't have to do math for it. When you see it, you get it, it's like, yeah, I get that, and I know most of my friends wouldn't.
You're making self loops, how do you know if you're doing an L or an R?
You have to specify.
Yeah, but like, how do you know?
Yeah, so you can parse this directly from left to right, so you should not need to go back left until you reach a final, or kind of the end of, you're gonna see a blank past the end of the input. Then you would know to terminate, go to the final state, move back left, or move right. It doesn't really matter where you terminate, where that read write head is when you terminate. Historically, people like the read write head to go back to something that is actually in the string and not the second blank that you would see, but there's nothing wrong with it. Is that an actual subreddit, Akiva? If so, I need to subscribe to it. It says there's r/unexpected factorial. That just sounds like a beautiful place to be. Yes, it's real. Excellent. How did I not know about this? Anyone with a solution? Yeah,
I just did, two states, and then so for Q1, that first initial state I have, if it's blank, put a 0, then move right, and then also on that same self loop, if there's a 0, put a 0, move right. And then eventually when it runs out of zeros and it's blank, then it'll go blank, blank, blank.
the first one you said, if there's a blank right at 0, move right. That sounds like it's gonna infinitely fill the tape with zeros. As soon as you see your first blank, as you're moving right, you're gonna write a 0 and move right. And you would continue to do that for the infinite number of blanks all the way down the tape. So I think when we see a blank, that's gonna tell us we've reached the end of the string. So we need to go to Q1, and the question is now, if we're there in the first place, that means that we didn't halt and terminate seeing something else. So there should only be one transition on a blank, and that transition is what terminates us. But other than that, I think you're exactly right. So we'll start in an initial state Q0. When we see a 0, write a 0, we're not going to change what's on the input, but just continue to see the zeros and move right. But we do need to see a 0. How do we guarantee that we see a single 0? Because if we do something like this, then we could just immediately see the blank and go and accept. So how do we make up for that?
See another 0, we go back to Q1 or Q0.
Okay, that could be. I am now thinking that 2 is the wrong number of states for this, and the answer really should be 3. Because we need to move to a state when we see our first 0 that says we've seen a 0, and then we can loop from that state for any number of additional zeros that we see, and then go terminate when we see that. So I think this is wrong, and I'm going to change this before I upload it. How have I taught this class 3? I think I stumble on this every time I see it. Tell the class, I'm gonna go fix this, and then forget about it.
Technically, it's 2, because you don't count the first state.
if you don't count the first state, the initial state, but I would count the initial state. So I think 3 is the correct number of states. So Q0 on a 0, we're gonna move to Q1. And then from Q1, when we see zeros, we'll stay in Q1 until we see the blank, then we move to Q2 where we accept.
Would you just write that as 0 then to an R?
Yeah, so if I'm fixing this,
Why
this
can't-
should be Q1 on a 0, then we would have Q1 to Q1, so that's wrong. Then we have, this would be Q1 as well, and this would be Q2, then we need one more transition on a Q1, seeing a 0, going to Q1, 0, right?
Why can't you have Q1 be the trend or the accepting state and then loop back on itself and then have the blank state? Go back to Q1. and-
You really could, you
Okay.
could,
That's what I have.
yeah,
The
that,
first state just sees the first 0 and then Q1 sees
Yeah.
0 star.
yeah. That would work because there's no other,
0, 0 star, which means 0.
I guess now if we allow 1 in the alphabet, that's what's gonna cause an issue, because then you halted when you saw the 1 and you're in a final state, so you would accept.
Yeah.
So if we allow for other characters, the only way to get to a final state should be now we're there and we're ready to accept, even if we see something that we don't expect.
Mhm.
So the very last transition, either moving back left or right at the very end. Usually in a Turing machine, you want that final state to not have any logic in it.
I see.
But yeah, if the alphabet is just zeros, no problem. Questions? We ready for a harder example? That I don't think any of the others are gonna have mistakes in.
Is there any way if you could just do the NPDA for it, or the?
You absolutely could. You could write a DFA for this since it's a regular language. But I definitely wanted to start with something that was easy enough to imagine a language where there aren't too many transitions. If I give you a language that's not context-free, then there are gonna be a lot more transitions associated with a Turing machine. But yeah, you could easily make a DFA for this, an NPDA for this, anything that we've studied so far, because the language is simple enough to do that. Question, here is example 2. Let's do a context-free language. A to the n, b to the n, for n is greater than or equal to 1. So we need to see at least one A followed by B. First thing you might want to think about before you dive in, think about the string on the tape. Before you start making the Turing machine itself, just think about how would a Turing machine be able to handle this? Because we're not going to be parsing this in a single string left to right. We're going to have to be doing some kind of bouncing around to be able to map an A with a B, an A with a B, an A with a B, an A with a B. Because you don't have a stack that you can just push to. You either have to create your own stack on this tape, which would be really hard, or is there something more clever you can do?
Well, it's A to then B to then, so we have to see A's and then B's.
Right.
So it has to be that exact order.
What if it's 3 A's and then 10 B's? How would can we just say, we've seen some A's, as soon as we see our first B, see some more B's, that would work, but we also need to pair the A's with the B's to say for each A, there's an associated B. Really easy if you have a stack defined for you already. Less easy, more difficult if you have to create your own structure and or think about how can I solve this without a structure when you can move both left and right.
Do you need to do multiple passes of the whole string, left and right?
Awesome. That's one possible way to go about it.
The need to end in a halt.
Yes,
Oh, okay.
we need to be able to terminate and say either yes or no. This string that's on the tape adheres to this language or does not.
In the previous example, you started by defining state transitions. Did you start by drawing a diagram of this, or would you like just? recommend-
Possibly. I don't know if I would start with a state machine necessarily, but I would start with imagining it on the string and then saying, all right, if I can look at particular characters rather than defining the transitions of how do I go about, think about if you were this system that can move and read left and right, how would you algorithmically do this with just those tools? The key insight to this will come from remembering that you can change the symbols on the tape. This becomes important because you need to differentiate between an A that you've already seen and parsed and mapped to a B and ones you have not. B's that you have seen and mapped to an A and those you have not.
Can we add characters that aren't in the language?
Yes.
In the tape language? And
Yeah.
then replace?
Yes, so the tape language is distinct from the input language.
So you
or at
could have
least
like
can be.
a sub,
Yes,
something.
yep. You can write whatever symbols you want and just define that to be the tape alphabet. In my example, I will use X and Y, representing A's that have been seen and B's that have been seen. Let's all get on the same page and then I will set you loose to finish the transitions. So start with the leftmost character, ask the question, is it an A? If it is, replace it with an X. This is an A that we have seen now. And the next process, the algorithmic process, is going to be to move right until we see a B that is going to map with that A. When you do find that, replace it with a Y, saying, I now have mapped some A that I've already seen to this B that is now a Y. Once you do that, move back left until you see your first X. When you see an X, move back right and look for the next A. If that's an A, turn it into an X, and then repeat that process. If you've ever turned an A into an X and you move and you never see another B, you see a blank instead, you can halt and reject. That means there were more A's than B's. On the other hand, if you are done mapping X's, when you move back to try to find the next B, you move back to and you see your first X, and you move and you see a Y now instead, you're gonna need to go check the end of the string to make sure there aren't more B's that haven't been turned into Ys. It'll help you if you try to write these transitions as groups. Think of them as kind of like you're writing an assembly program and you have either go-tos or blocks that is, here's the start of a process. And when you say go to a particular process, that works kind of like a method in assembly. Blocks of related transitions.
We can reject on a non-halting state.
You basically define that, yeah, you would say, if no transition is defined, you immediately go to a halt. Yeah, so you do not have to make this a total function.
Mhm.
This would be disgusting as a total function. Might take you a little while, talk to your neighbors, see if you can crank this out together. Or work alone if you would prefer to. Anyone have questions or having trouble getting started that I can help with?
Shouldn't you move the read write head right until you see the first B in the second step? Because if you move the read write head left off, yeah, you'll go into infinitely square
Hopefully
shapes.
there's an X there.
Oh, okay.
Yeah, you're gonna go until you see an X and then move right and look for an A.
So the first, when you start the program, you turn the first A into an X.
Yeah,
And then you go left until you hit the X and then you go to
Yeah.
the B, okay.
Yeah. Yep.
you're doing the walking, right?
Yeah.
So we're having to go along.
Yeah,
And we're gonna suppose that there's more A's than B's for whatever reason.
Sure.
And so we're going to walk along and we're gonna keep seeing the Y's, because we've already gone through all of the B's and we're gonna run out of the
Mhm.
Y's and we see a blank.
Right.
So you're in some state and you read, do you have to write a state transition then? that
no,
goes
because you would
from-
immediately want to halt and reject at that point.
So you just don't make a state for if you read a blank, right? You're just gonna assume that it's.
Yeah. Yeah, since you haven't hit that final state yet, then you would be halting at that point, since we're not in the final state and reject. Yeah, so you do not need to worry about if you hit a blank while you're looking for a B. If you don't define it, that's gonna immediately lead to failure.
Go from a B and we're looking to the leftmost X, then we go right and we don't see an A. Then we know.
Well, then we know that we mapped A's to B's. So the very first process that we do is mark the A. So if we go right from our first X and we see a Y that was a seen B, then that would say we've seen A to the N, B to the N, but we still now have to go to the end and verify, are there any more B's at the end of that? Because you could have a series of X's, a series of Y's, and then a B or more B's at the end that would be representative of more B's than A's, and then you would want to reject. Only if you go past all the X's and all of the Y's and hit a blank, then you would accept.
Okay, so I'm just thinking, so if we see an adjacent Y to an X, then we go, and if we see anything other than a Y or blank.
Yeah,
Okay.
yep. They aren't as easy as they first appeared, are they? Even a simple thing like A to the N, B to the N is quite a few transitions.
We can have a heap and then have random variables to name
Yeah.
to declare these, the whole numerical that always evolves. And if we read it, we can then compare the two numbers.
I think a class like this really makes you appreciate how structured the programming languages that are out there actually are, because you start to break it down and you realize that data structures, when you instantiate something like, I can just make a hash map, great. Well, understanding what that is it's a complicated structure. It's there for you to use, but how was it created? How was it programmed? And then breaking that down further, how are the components of each of those represented and processed? And eventually you can break down logic as far as something like a Turing machine. And I think assembly is the first time that you really start to appreciate that, when you see what a lot of programming languages are translated into. But Turing machines are kind of the abstract version of assembly in that sense, where you break it down just directly into the pure logic of what are we reading? How are we choosing whether that is what we're expecting or what we aren't? And a lot of that work is done at the low level and optimized and put together into a large package where you can just write code. It's really amazing to me. To this day, I've been a computer scientist for a long time at this point, but it still blows my mind, just the sheer amount of work that's been done to make what we can do on a daily basis possible. How it all works.
I think the whole concept of the tape, not having like specific memory addresses and stuff, and having just, you're basically just moving in space and you're having to be
Yeah.
relative to everything else.
Yeah.
I mean, whenever someone came up with the concept of, wait, we should actually organize these in a way that we can correctly access them.
Yes.
That's pretty neat.
Then you account for stuff of all the EEs that had to figure out the circuitry, then build the boards, then
Mhm.
and make everything talk to each other. On top of the fact that then it now has to go up from the layer of electricity to represent binary, to then represent assembly, so on and so forth. The amount of layers to this onion has an entire city inside of it.
Yes, absolutely. How do you error correct bits that are accidentally the wrong bit? That's why we use binary, is it minimizes the likelihood of errors where zeros are ones and ones are zeros. If you had a high voltage, medium voltage, and low voltage, you would exponentially increase the number of errors that you have.
Black and white.
Yeah, as soon as you can do 1 and 0, it minimizes that. You can't really do more than that.
It's office charge.
can't
or
do
it's below
unary.
this charge.
Yeah. But the errors do still happen. And there's something underneath the hood that,
Corrects.
that identifies and corrects.
Thank you, EEs.
If you see an electrical engineer, just thank them.
I do, because you had to do differential equations to figure this out.
Yeah, Akiva says that 3 blue, 1 brown has good video and error correction algorithms, Hamming codes, etc. I remember taking those classes. I haven't really done too much with that since I was an undergrad, but learning about that really made a big difference. Understanding how actually voltages are used to represent ones and zeros, and how that mapping allows us to do the complicated work that we can do. All right, let's get an answer to this. I think most people have either come up with an answer or gotten stuck. So let's take a look at first group 1. Here are the transitions for converting an A into an X and moving right till we see a B, converting that into a Y. So we have state Q0 that just says, where do we begin? We look for an A. If we don't see an A, we immediately halt and reject. We have to move to Q1 at that point because now we don't want to replace an A with an X. When we see an A, we want to keep those A's on the tape. So we need to be in a different state to be able to do that. We said that Turing machines are deterministic, so we can't have non-deterministic transitions like if you see an A, either convert it into an X or skip over it. We cannot have something like that. So we need to differentiate the states for that. Q0, we're looking for an X, an A that we're going to turn into an X. In Q1, we're looking for A's and we're keeping them there as we move right. So we're going to loop that every time we see an A, moving from Q1 to Q1, skipping over all the A's, right, until we see a Y. As soon as we see a Y, we're going to leave that Y and we're going to turn we're going to leave it until we see our first B. The reason we need that Y there is because this is not necessarily the first time. This is going to be a general algorithm for moving forward and seeing the first B. And some of those B's may have been converted to Y's already. So group 2 then is just returning to that leftmost A. So we know that we are starting at a Y. So we're going to move left from that Y. We're not expecting to see any more B's because we've turned all the B's to the left of that Y, into more Y's. So we can move left on Y's, left on A's until what terminates this idea is we see our first X. And this loops us back to Q0, where we were when we said, we're now going to take our first A and convert it into an X. Because if we move right, when we see our first X moving left, what's going to be right of that is the next A. So we're back in Q0 looking for that next A. That should ping pong back and forth, mapping A's to B's, A's to B's, A's to B's, A's to B's. What does termination look like? We just say from Q0, if we see a Y instead of an A, that means we've run out of A's. So we're going to move right past all of the Y's. So we first transition from Q0, because Q0 is not expecting any Y's. If we see a Y there when we're not expecting it, that's going to halt and reject. But Q3 will be, now we're moving toward termination. We're going all the way to the end of the string. We expect to see nothing but Y's until we hit our first blank. If we see any B's, or if we see any A's, then we halt and reject. Any questions on how this machine works? Take a minute, just take a look at it, try to visualize what this is doing. Compare what you did to what this says. And see if it makes sense.
I didn't see the similarity between where Q0 is used the first time initially and when it's reused for,
Yeah.
made a different state.
Yeah, and that's totally fine. It's a little more complicated than it needs to be, but it would be correct.
Got like 95% the same thing.
Yeah, that's great. That's a very good place to be for your first real Turing machine program. The regular language one from before was kind of a, do you understand it? Because there are so few transitions. This is the first one that really requires deep thinking to pull out the program. And even then, it's still A to the N, B to the N, which is a really simple language. It's a complicated Turing machine, and you can see just how much work it is to produce a valid Turing machine program for even simple programs, which is why we have real programming languages, and we don't program with a Turing machine.
So your state Q4, that's the final statement?
Yes,
Okay.
yeah, that's the final halt and accept state.
And you still move, you have the right move on it?
Yeah, just because it has to be defined. You could either move left or right there. I actually probably honestly prefer left, but I borrowed these from the book, so I wanted to make sure that I was consistent with the book.
The only difference I had between the actual answer and what I had was I had an extra state because I was confusing if it could be a B at the very end or not.
Gotcha.
The only difference.
Yeah, and if you see it, we don't need to handle it because it's not what we expect. So we can just ignore it and let the partial function handle.
Throw up an error on the stack, crash the whole thing, kill the process.
Throw the Turing machine out the window.
It grows legs, pops out the window.
So let's actually go through and see if we can find instantaneous descriptions for this string AABB. So I'm gonna go back to the last slide, but let's actually go through and parse and show instantaneous descriptions. This might be a little long, but let's take this program with the string AABB and come up with some instantaneous descriptions. So what would the first instantaneous description be? What is the state of this Turing machine in instantaneous description form? We're at Q0. The read-write head is pointed at the A. So what is that first one?
Replace it with an X and move right.
So the initial state of this is we're gonna have Q0 followed by AABB and turnstile. This just gives us that state. We're going to, where is the state? We were gonna say that everything that the state is pointing at and after comes after that state. So we're looking at a string that tells us what's on the tape and where are we.
X Q1 ABB.
Yeah, so the very first thing we're gonna do is we're gonna change this A to an X. And since we moved it right, the first X comes before Q1, followed by the ABB that's left on the tape. Continue this process. See if you can finish this off. There are gonna be a good few of these.
So for the subsequent instantaneous descriptions, you don't have to say where the read-write head is, you just say the state.
Yeah, this already tells you. This tells you the read-write head is pointing here. This tells you the read-write head is pointing here. Cool. arrow here is not necessary. I'm just drawing it to identify where the read write head is.
U2 YB or XQ2A YB?
That's X Q2. And then Y,
A YB.
Q2, there's still two A's, so I think we're now past the A here,
Yeah,
pointing at the A, and then Y.
okay.
Yep. Anyone with questions about anything that I've written up here, at least getting us started? Everything at the moment, there's the final answer. As mentioned, there are quite a few of these. But since we are basically out of time, I wanted to make sure you at least had an answer. We'll probably come back and look at this at the very beginning of next class before we get a little bit more experience. I think there might be one more example after we talk about a little bit more. And then we're going to start talking about variations of Turing machines, because working with a single tape is kind of annoying. So what kinds of Turing machines could we design that have exactly the same power as this standard Turing machine? What kinds of Turing machines could we generate that don't have that same power, either have less power or more power? If more power is possible,
Anything that's
Question mark.
complete.
so we will come talk about that. This becomes one of the most interesting abstract concepts, at least to me, in the entire class, just talking about what is that boundary of what we can theoretically design that maps to logic that we can create with some kind of digital machine.
I mean. Basically, the game of life with a Turing machine.
Yeah.
At least one.
We'll talk about Turing complete systems, of which the game of life is one of them.
I look forward to, yes,
Have we heard of the concept of Turing complete machines before?
Turing complete
Turing complete
basically means anything that is Turing complete can be a Turing machine itself.
And can simulate any other Turing complete system.
There-
So we have proofs out there that the game of life is a Turing complete system, which means that you can simulate the game of life within the game of life.
Yes,
A paper was released a few years, probably more than a few years ago now, that proved that Magic the Gathering is a Turing complete system. So you can use the game of life
it is
to
on.
play Magic the Gathering. You can use Magic the Gathering to play the game of life. You can use Magic the Gathering to simulate Magic the Gathering.
You can also now build a computer with Magic the Gathering.
Yes. People have done this with Minecraft. Now do it with Magic the Gathering. Simulate a CPU with Magic the Gathering and its rules. It is possible.
It'd be very, very soon.
Yes,
Yeah.
it would be really fun to see that design. Really, really complicated, but interesting.
That means Minecraft Terraria as well.
Yeah,
Someone
yes.
made a computer.
Yeah,
in it.
yeah. I love open world survival craft games for that reason, that there's just so much freedom. And then that freedom maps to a lot of what we look at in our, in fact, if you're curious, I'm gonna bring this up now and show it to you, because we're gonna talk about Turing complete systems, but this becomes kind of the time that I can start doing this. I want to, for those of you who have to head off to something, you're welcome to do that, but I'm just gonna quickly show something here. See, it's. So for those of you, this doesn't actually require the bad music, but for those of you who are familiar with the game of life, get this out of the way. This is just eventually gonna zoom out.
Okay, when I thought the game of life, I was thinking of a board game.
Yeah.
I don't know what this is.
No, this is the game invented.
Conway's Game of Life, yeah.
Is some
So these are memory blocks, right, ones and zeros?
These are
Represent
essentially
memory blocks?
cells.
Yeah.
And these cells can change based upon the neighbors and adjacency
Yeah.
of which cells are living and which are not.
Oh, is this one of those things where it's like each square has like 3 different rules to
Oh, I see.
decide whether or
Yes.
not it's like, yes.
Yeah.
Oh, okay, I think I've seen this, it's in like Minecraft. Like in a Minecraft snapshot.
So now I just want to know the proof to make sure something is Turing complete or not, because now.
Now sped up a bit, but.
Because it takes a while to get to this point.
See it, thank you.
Yeah.
Process how we needed to actually.
Yeah, so it's really short, but that's the basic idea of emulating a Turing complete system within a Turing complete system. It just happens to be recursive, the game of life emulating the game of life, but that works for any system that we can prove is Turing complete.
Then makes me ask, is Turing completeness part of the infinity that is the number of irrationals between 0 and 1, or is it boundless?
We will talk about that.
Because that makes a difference on the infinities.
Yes.
Because
We will talk about different infinities and how some infinities are larger than other infinities.
what's the very tattoo from here, if you want to bring everything, it is really fun when you realize just how broken everything is.
There is a system embedded within this madness, but it is madness.
And we can prove it's madness,
Yes.
why it's so mad.
Yes.
And that's what makes it hilarious, but we can't prove it's
All right, I'll see you all tomorrow.
but we can't